All right, welcome back to statistics. And today we are going to start our journey into tests of hypothesis. This is chapter 9.1. Okay, let me go ahead and share my screen. The nice thing about chapter 9.1 is it's kind of late on actual math. Okay, there's a lot of reasoning involved here, but the math parts are a little bit low, a little bit light. So let me just start us off with what is a test of hypothesis first, and then we can get into the problems, okay? So there's a couple of things we got to talk about. One is we have to talk about types of errors, okay? So what I usually do is we draw a little diagram here. Okay. And what we're going to do is we're going to come up with a jury verdict here. Is a pretty typical way of describing test of hypothesis. And then we're going to have the truth here. Okay. So I'm going to go with the American system in the ideal. Okay, it's reasonable to say that's not the way it is. Like I get that. So when we talk about what's going on, like what is your presumption as you go into court? Okay, it's supposed to be that you are presumed innocent. Okay, so the presumption is we're innocent. We're going to call that the null hypothesis. Okay, and the alternative, I usually call it HA for the alternative hypothesis. But I think your book uses H1 for alternative. Okay, so I'll try to go with H1, but I'm going to slip. Okay, I'm going to call it HA, and we get not innocent. Okay. But the jury doesn't actually say innocent, right? They say you're not guilty. Okay, and that's another thing we'll get into is the language of what's going on here. But right, the truth could be, right, you're innocent, and the jury comes back and says, I agree, you are not guilty. Okay, but the truth is, you could be innocent, and we could have a guilty verdict. Okay, that could happen. The truth could be that you are guilty. You did it. Okay, and you're the only one. Well, you're probably the only one person that knows, and the jury has to watch you and the prosecutor and the defense and make a decision, and they can come back with not guilty. Okay, or you could be guilty, and the jury could come back and say guilty. So here, there is no error has been committed, right? If you're innocent and the jury comes back and says we have no error, okay. But if the null hypothesis is true, you're innocent, okay, and the jury says no, we reject that. Okay, we're saying you're guilty. What happened here was the null hypothesis was true, but she rejected it. Okay, so reject HL, reject the null hypothesis. We're going to take our alternative. Okay, so this is called a type 1 error. Okay, and then we'll get into that. So what happens with a type 1 error, right? Is you put the guilty person in, you put the innocent person in jail. Okay. We could also have a problem where if it's somebody's guilty and the jury comes back, no, not guilty, you didn't do it. We have committed something called a type 2 error. Okay, statisticians are famous for naming things in creative ways. Okay, so in this case, you've set a guilty person free. Okay, now normally we're supposed to clamp down on the kind of thing where we're sending the innocent person off to jail. Okay, and that's where this alpha comes in. Okay, remember all the alphas that we did in confidence intervals? This is the alpha. This is the probability of making a type 1 error. Okay. And again, in our famous way of, or famous penchant for being able to name things, type 2 error is called beta. This is the probability of making a type 2 error. Okay, and there are ways to calculate this too, but we don't do them in this class. Okay, so alpha, the same alpha that you met before. This is the probability of making a type 1 error. And it's not just like the errors have to add up to anything, right? There's no relationship here to equal 1 or anything. I mean, they will equal something, but there's no rule that says it has to equal something. Okay. And here's one of the reasons why. So if we have alpha, right, this was the chance we send the innocent person to jail, to prison. Okay, beta. Okay, we let the guilty go free. All right. Now, you really don't want either one of these errors to happen. Okay, but here's the idea: if you clamp way down, it's like, look, I never want to send the innocent person to jail. Okay, so we're going to take our alpha and we're going to squash it. Okay, we're going to make it really, really tiny. We're going to make it really hard to send an innocent person to jail. Well, you're going to raise the bar on the prosecution really, really high. Like, you can't deal with eyewitnesses anymore because eyewitnesses have too much error, too much uncertainty. Maybe we should anyway, because that's the standard is like a reasonable doubt. Okay. Anybody, jury ever asks you, say we want 5%. Okay, that's the probability that we want to make that error. So that's what lawyers usually go with, is 5%. Okay, I know in practice none of this is true, but we're going to pretend that it is. Okay, so if we clamp too far down on this thing, right, we are going to let a lot of guilty people go free because they didn't. The prosecutor can't get to the level of evidence they're requiring to squish this alpha all the way down. Okay, so it has to be some possibility for us to do this. Okay, hopefully it's as low as reasonable. Okay, I don't want to be standing in court and having somebody say, "Well, they did it," like I didn't do anything. Okay, and hopefully I will never have the experience to scream at the jury, "You've made a type 1 error." Okay. Conversely, right, if you want to say, "Well, I've had enough of crime in this community. If the police picked him up, he must be guilty of something. We're gonna send him to jail." Okay, so if you want to squash down on this, like anybody who's even remotely guilty, like they're not going free. Okay, you want to squash down on this, then you do get the police picked him up, he must be guilty of something. So you're going to send a lot of innocent people back to jail because maybe they got the wrong person. Maybe they got the right name, but it was the wrong person who did it, right? They got a warrant. It's John Smith. Like, right, there's only one John Smith in our neighborhood. That's him. Like that's not the way that works either. Okay. So there has to be a balance between one and the other, just like the confidence intervals, right? If we did like a 90% confidence interval or 95% confidence interval, you got a reasonably wide margin, but it was still small enough to be able to be making sense out of it. Whereas if you ended up with like, I had like 100% confidence interval, like, well, all I could tell you is it's a number, and that's not useful. Okay, or 99.9% confidence interval. I don't know what they actually did use. But usually when this happens, if your interval is so wide that this defies being able to make use of it. Okay, so if we have like a huge confidence and I'm like, hey, your car repair bill, it's going to cost you somewhere between $200 and $1,200. Great, I can't budget for that anymore because I have no idea what this is going to be. All right, so I would rather go with your ability to miss is a little bit higher. Okay, but it gives me a narrower region, so I've got something better to plan on. Okay, they're nonlinear things. So the same thing is going on here. We squish alpha too much, right? We're going to send people that shouldn't go to prison. And you squish down beta, okay, and you never let anybody, everybody who gets hauled in front of a judge is obviously guilty. Well, you're not going to let any people go free, but you're going to go in the other direction. Okay, so alpha gets squashed down. Your standard of evidence is really, really high. You're going to let people who should go to prison out. Okay, but if you squish down on beta, you're going to send a lot of people that shouldn't be in prison to prison. Okay, so there has to be a balance. All right. So that's the error out of the way. By the way, I have never asked a question on a quiz where you have to memorize a type 1 error versus a type 2 error. There are other classes. If you take psychology, statistics for psychology, you're going to be doing a lot of this. Okay. If they had better names, I'd feel a little bit better about asking you a question. But to just be aware that there is a type 1 and a type 2 error. Somebody brings it up, you might have to say, I heard about that. Could you explain what that is again? Okay. And usually they're going to use the trial case type of a thing because it's not like, law, courtroom cases, dramas on TV are rare, right? We all have experience watching Law and Order and NCIS and all of that stuff. All right. Back in my day, it was like Quincy. All right. But that's what we do. All right. So there's actually a type 3 error. This one's easier to figure out. This is, you asked the wrong question. Okay, I think that was John Tukey. Okay, so this would be the analogy for this one would be like, you get hauled in front of the judge, they arrest you, and maybe the crime you're charged with is like armed robbery, and they say, well, we have arson. You've burned 20 buildings. Now that may or may not be true, but that's not what their evidence. That's not what they're bringing you into court for. So you've asked the wrong question. Charged with the wrong crime. All right. So we have steps. Okay. For a test of hypothesis, we have steps. Okay. We are going to state our hypothesis. And since this is statistics, we deal with numbers, we're going to state our hypothesis in terms of numbers. Okay. So we have a null hypothesis. Okay, this is the status quo. Okay, if my cereal box says that there's 16 ounces of cereal in this box, that's the status quo. That's what the manufacturer said. Okay, if I get my computer and it says this memory card is good for 300 hours, 1,000 hours, whatever it is, my whole hypothesis to say it's 1,000 hours. Okay, if you are looking at if you're testing your water supplies and the water, the people who test the water said the water is safe, my null hypothesis is there is a safe level of lead in my drinking water. Okay. Now the alternative hypothesis, okay, that's actually what you're trying to prove. Okay, we're given the benefit of the doubt to the null hypothesis, but what we're trying to prove is what your alternative is. Okay, that's what you like to say. Like if you're a drug testing type of a thing, like this cholesterol medication is no use or doesn't have any difference in not taking any medication at all, right? Taking the medication, not taking the medication, your cholesterol remains the same. Your null hypothesis, this medication lowers your cholesterol, okay? Or well, the government said that there's a safe level of lead in my drinking water. My hypothesis is there is not a safe level of lead in my drinking water. Okay, and we're going to test it and see. One thing I would say as a piece right here is we're going to state our tolerance. Okay, what chance would you like to make a type 1 error? Okay, what chance would you like to say, okay, we have the null hypothesis and I'm going to reject it. Okay, what is that probability? Okay, so we're going to state our alpha here. Okay, this is not in the book. This is just my preference. I've seen people who, and actually some books don't even have you state an alpha. They just have you tell the reader what that is and let them make the choice. Like, don't let the reader make a choice. Okay, there's meetings on this, on what your alpha ought to be. Like if you're doing a drug company type of a thing, or doing environmental, the government will tell you your alpha is, and that's the standard we're going to deal with. Okay, because legally that's what we're required to do. But if it's up to you, right? You're trying to make a policy, or your company is trying to do something, then you guys are going to have a meeting. Like, what is our acceptable alpha? What's the probability we're going to make a mistake? And how tolerable is that? And you always have to go back to remember, like, if you clamp too far down on one, you're going to let the other one in. Okay. So you can't, when you do this, to say, people who haven't had statistics, you're going to say, well, what's our acceptable error here? We'll say 0. You can't do that. You open the door up on the other side too much. Okay. So realize that there's going to be some amount. Usually that's 5%. Okay. We did 95% confidence intervals, 5% for test of hypothesis. Okay. That's the academics. That's pretty much our standards here. All right. In a different field, you may have a different standard. That's fine. Okay. But usually people have thought about this and agreed upon it. So you're not really ever on the hook, like, by yourself to figure out an alpha. Okay. But you can change your alpha, and that changes the result of your experiment, right? If you say, well, I need to be, I want to say that 5% is acceptable, and it comes out like, well, this was a 4.5%. It's like, I think 3% is acceptable. We're going to go ahead and change the results. Okay. You don't want to do that. You want to put it at the top. So at the end of the problem, you're looking at your alpha, you're looking at your values, and you can compare it to what you started off with. Okay. You don't want to let that linger. It's like, well, I'll make that decision later. Like, don't do that. Okay. You're going to get in trouble. It's not going to work well. Okay. Third thing is we are going to go ahead and calculate our test statistic. Okay, just like in confidence intervals, right? There was a different formula for every different kind of confidence interval we're going to deal with. Somewhere in the world, there is something called the Big Book of Test Statistics. Okay, and it's got a different formula, a different calculation for every single test statistic and every different possible permutation. We're dealing with 3. We're dealing when sigma is known, sigma is unknown, t-distribution, and proportions. Okay, so those are the problems that we're dealing with. So it very much mirrors what a confidence interval is, except it's kind of like the other side of the coin. It's like, can you phrase your answer in terms of a question, kind of a thing. Okay. And then 4, okay, we're gonna make a comparison. Okay, so we're gonna make a decision. Okay, and this is the easiest step of all. You're just gonna look at your test statistic and see what that probability was compared to your error, and then draw your conclusion from that. Okay. Number 5, we're going to write our conclusion. Okay. Yes, you have to do this. You have to write a sentence in the context of the problem. Okay, so you're going to write a sentence in the context of the problem. Okay, a lot of stats classes, they just let it go with like, oh, what was our decision? Well, we rejected the null hypothesis, so reject HL. I guarantee you, in 1 month, you're going to look back at that. You're going to, assuming you're looking back at your statistics homework at all, you're going to look back at that. You're going to say, reject HL. What was I doing? It's like, you have to write it as for somebody who has not had the class. Okay, so if you reject the null hypothesis, you are tacit. You're not really accepting the alternative, but you have no reason to say that that's wrong either. Okay, So if you're talking about, the government says, hey, there's a safe level of drinking water, safe level of lead in your drinking water. You say reject HO, like, what's that mean? Like, assume, maybe you went to a community board and you're like, we're all worried about our drinking water. So we look at this, we did our test, we rejected the null hypothesis. And they're going to stare at you like that's absolutely useless. So we're going to say, there's evidence to say there is not a safe level of lead in our drinking water. Okay, now there's like a real formal way to say this, kind of like what I just did, and then there's a far less formal. You say, I think there is too much lead in our drinking water. Here's my result. Do something about it. Okay. So if you're allowed to write a sentence, please, I know English is not the precise language, okay, that French is, that math is. So you're allowed to take a little bit of liberty with this, okay, to express yourself. Okay, so this is when you're doing this by hand, it's like one of the very few times you get to say, I'm creative in math class. Okay. When you write your reject HO and state what your conclusion is, okay, write something that's going to make sense in the context of the problem. Okay, and then we're done. That's it. Those are your 5 steps. The calculator is going to take care of a lot of this. Okay. But I also, like, if they don't say, okay, alpha is 0.05. Okay. If they don't say it, that's what it is. They will usually say it. Okay. But you don't want to, I did, there's some books that will just say, well, we just calculate the p-value. That's part of this right here is getting our p-value. And we're just going to let the reader choose. Don't let the reader choose. Okay. They'll never, they won't choose correctly. Okay. They'll think, well, 50% is not too bad. Like, no, 50% is terrible. Don't do that. 5% is correct. You choose. Okay. You're writing the report. Or have your committee choose, right? Have your group choose what alpha should be. Don't leave it up to the reader. Okay, it'd be like saying, well, you can pick whatever confidence interval you want. I mean, technically, that's true. You guys were going to discuss, like, what's the probability of being wrong, and what are those consequences? Okay, that's how we pick. All right. So one of the things we're going to do here, okay, this is how we write a hypothesis. We state our hypothesis. We're going to say that HO, by the way, the null hypothesis always gets the equal sign. So we're going to say the mean is 7. Okay, so maybe we are buying packages of, maybe we're buying a package of cookies, and we want to say that the package of cookies is 7 ounces. Okay, and your alternative hypothesis is it is less than 7. Okay, I feel a little shorted. Right, nobody complains about getting too many cookies. I feel a little shorted in this scenario. Okay, so this is called a one-sided test. All right, so you're buying a treat and you find that it feels like it weighs less than it does. So you've got a whole bunch of that treat, you weigh them, and then if you find like, hey, there are less than 7 of them, okay, then we're going to have a problem. But you're trying to test, you're trying to show that I feel a little cheated. But this is what they call a one-sided test. You know what a two-sided test looks like? It looks like this. Mu is equal to 7. Again, HO always gets the equal. HA, mu is not equal to 7. Okay, that means it could be above or below. I'm not really quite sure. Okay, there's usually a more robust test. Okay, but there are plenty of times where a one-sided test is the appropriate thing to do. Okay, so the alternative hypothesis. Okay, so this is what tail are we looking at? Okay, so we want less than, right? We want less than. So we're looking for probabilities over here. Okay, so it is a one-tailed test, and we are looking for the left-hand side. Okay, so we want a left tailed test here. All right, and then we should be okay. Again, I'm actually not really going to ask you a lot of these questions on a quiz. Okay, so if you're looking up and you're saying, "Oh, I need that little table to help with the type 1 error, type 2 error," like that's fine. You're not going to be tested on it. You're not going to be like counted on to memorize what those things mean. Okay. The point of this is so that when somebody says, "Hey, you committed a type 2 error," you know what they're talking, or at least you know that there is such a thing and not just making it up. Okay. So let's see here. Type 1 or type 2 error. So we have a test is made of HO mu is equal to 60. Okay, or H1 mu is not equal to 60. Okay, so our hypothesis is going to be set up mu is equal to 60. And H1 is mu is less than 60, right? That's what they said. So again, left tail, one tail test, left-hand side. Okay, same scenario we had before. But they said the true value, okay, we have the true value of 58, okay, and HO is not rejected. Okay, there's a table in your book that pretty much goes through exactly the same thing. So you don't, feel free to make your own table from my values here. Okay. So the truth is, right, that HO, that the null hypothesis, the value was actually 58. Okay. And they didn't find for the alternative. They did not find for guilty. They said, this one is true. Okay. But we said, right, the test said that that's not true. Okay. So what the jury found was like, no, that's not, it's you're not guilty. It's 60. Okay. Because that's the null hypothesis, right? It's 60. So the jury comes back and says, no, it's 60. And you're like, actually, it was less than that. So you were guilty. But the jury came back and said not guilty. So this is a type 2 error. Okay. Okay. Yeah. All right. By the way, I have to reason and logic my way through these things too. So if you're looking at it like, wow, this seems a little cumbersome to kind of explain, it is. Okay. So that's, there are statistics classes, it's probably morph into one, that we spend a lot of time like trying to put context into what this is talking about. Okay, so math department statistics usually concentrate more on the calculation parts, but psychology-based statistics usually spends more on the interpretation parts. Okay, so let's see here. We have a sample of 100 flounders of a certain species. They have a weight of, these are tiny flounders, 25.5 grams. Okay, scientists want to perform a hypothesis test to determine how strong the evidence is that the mean weight is less than 24 grams. Oh, I hate questions like this. I don't want to say that it's strong or weak. I just want to say it's this one or that one. I don't, just because you get a lesser number shouldn't mean that it's like a stronger or a weaker thing. Okay, it really shouldn't. So, bugs me. All right, scientists want to perform the test to see how strong the evidence is that the mean weight is less than 24 grams. So what we're going to do is we're going to say that the status quo, right, we think that they have a mean weight of 25.5. So mu is equal to 24 grams. We're trying to test. We're trying to test that it's less than that. Alternative, mu is less than 24 grams. Okay. Now, that's what it seems like to me when they ask this. If they're going to say 25.5, I really don't have an argument against them because 24 is less than 25. And that's the thing that we have is 25. So I'm going to say 24 because it seems like that's the test they want to deal with. Okay. Okay, that was okay then. I interpreted their question correctly. Good. So they said they want to test about 24. We're going to write the test of hypothesis in terms of what they're trying, what the experiment or what their observation is trying to do. Okay, they want 24. We're going to write 24. Okay, Facebook reports that the mean number of friends an adult Facebook users is 338. Mine is far, far fewer. Okay, and I don't feel bad about that at all. Okay, a test is made of HO is equal to 338 versus a test of H1 equals to 338. If the null hypothesis is rejected, okay, so let's go ahead. We're going to say HO, right, is equal to 338. HA is mu is not equal to 338. This could mean that there's more than 338 or less than 338, because we're just saying it's not the same as 38. So we can have more or less. Okay. So it's a two-sided test. Okay. Remember, equal sign always goes to HO. HA was not equal. It's a two-sided test because it could be more, there could be less. I don't know. All right. So we say the null hypothesis is rejected. Okay. So this one, we're saying this is not true. So we're going to tacitly accept that. It was not 338. Was it bigger or smaller? Like, I can't tell you. It's just not 38. It's not 338. Okay, so we say there is enough evidence to conclude the mean number of friends is different than 338. Okay, that's all you're saying with this. Okay, that's all we're saying. Okay? You're going to need, and you don't. It's nice if you write this way. You don't have to write this way. Okay, so just realize that if you gave me a conclusion after you got this, you could say something like, you know, our test shows that that adult Facebook users do not have 338 friends. Okay, something to that effect. All right. All right. A company that manufactures steel wires guarantees that the mean breaking strength. Okay, it's a cool machine to do this, by the way. Because you put it in a thing and it just pulls on it until it breaks, and you can measure like how much pull it's been dealing with, how much tension it puts on it. Okay, but it just pulls it, it tears it right apart. It's so cool to watch. Okay, company that manufactures steel wires that has a mean breaking strength in kilonewtons. Kilonewton is a unit of force for SI. Okay, System International. So we have pounds. England Imperial has pounds. The metric system uses a Newton. Okay. Let's see here. Strength in Newton kilonewtons of the wires is greater than 50. They measure the strengths of the sample of wires and decide. So yeah, you don't just pick one. You have gotten a bad batch. You may have gotten an exceptionally good batch. I don't know. So we're going to say that HO, okay, mu is equal to 50, and H1 mu is going to be greater than 50. Okay, this is our hypothesis statement. Okay, I don't know what the alpha is. They didn't tell me, and they're going to tell me the conclusion, so it's not going to matter. Okay, so we're going to say that, hey, they said it was 50 grams or 50 kilonewtons. Okay, and I don't know why we would be trying to do that. We would actually be looking at the other side. If we were quality control, we would be worried that like nobody's going to complain. Like if your steel wire is like, hey, the breaking strength is 50, nobody's going to complain like, hey, your wires are too strong. Like, unless you're like cutting them or something, but no construction person has come by and going to say your wires were too strong, but we're worried about this. Okay, so the quality control part of me is looking at this like, I don't care if they're too strong. I want to know if they're too weak. But that's the problem we have. Okay, so again, remember, this is the one-sided test. We are looking at the right side of the curve. Okay, so they said it was 50. We are concerned that the average is actually up here somewhere, like 53 or 51. Okay, so if a type 1 error is made, what conclusion will be drawn from the mean breaking strength. So we're told that it's a type 1 error. Okay, what does the type 1 error say again? Okay, we have to go up here and look at our little chart. Okay, so we're saying the truth is, right? The truth is the HO is true. Okay, so we're going to write that down. We're going to say the null hypothesis is true. Okay, that's what type 1 error is going to do. The null hypothesis is true. The mean breaking strength actually is 50. Okay. And what did we find when we tested this thing? Maybe we just got a bad sample, or we got an exceptionally good sample. I don't want to go all the way up here. I want to go to where it says, there we go. So here's our HO, right? Right, in essence. And the truth was, it was good. But we found like, no, we're taking the alternative hypothesis. Okay, we're taking the alternative. So we're going to go back down here. We're going to say, nope, we have concluded. Okay, we have found, we the jury have found for the alternative. Okay, what's the alternative? The alternative says that the tension is actually greater than 50. Okay, so when I look back here, okay, type 1 error. If a type 1 error is made, what conclusion will be drawn from the mean breaking strength? The mean breaking strength is going to say we are greater than the 50. Okay. If a type 2 error is made, okay, so type 2 error is, okay, is that they're really guilty, okay, but we found for, so the alternative is actually true, right? Go back up to here. Okay, the alternative is actually true. The truth is they're, is guilty. The alternative is true. And we didn't find that. We found that the null hypothesis was true. This is why I don't ask this question on the quiz, by the way. Okay, so, but we found that the null hypothesis, actually, we're going to say the null hypothesis wasn't rejected. Okay, so to keep things simple as far as the language goes, I'm going to say was true, but in actuality, you're going to say something like the null hypothesis was not rejected. All right, so I know that's a little bit weird to take. This is another reason why I don't ask this question on a quiz. This will be just fine. Okay, so we found that the null hypothesis was true. Okay, so the conclusion is the mean breaking strength, right, is it's greater than 50. It's greater than, okay. Yeah. Wait, the alternative is true. We have found, and I'm sorry, I made a mistake. The testing has shown that HO, we did not reject the null hypothesis. So the whole null hypothesis was that it is still equal to 50. Okay, equal sign always goes to the null hypothesis. Glad I double checked. Okay, this test uses a one-sided alternative hypothesis. Explain why a one-sided hypothesis is more appropriate than a two-sided hypothesis in the situation. Okay, I hate this scenario because again, nobody complains that the tension is going to be too low. Okay, so with a one-tailed hypothesis, we can conclude that the mean breaking strength, okay, is equal to 50. With a two-sided test, we would not know if the breaking strength was bigger or smaller than, greater than or equal to, or less than or equal to 50. Okay, so that's actually a good reason to use a one-sided, because we really want to know. Is like, is it, if we failed, is it more than what they promised or less than what they promised? And with a two-sided test, all we know is it's not the same as what they promised. Okay. Well, maybe I retract my include, oh, they want to say greater than? All right. All right. Like I said, for me, it's like maybe the quality control person on the you've got the wire, you're sending it out. You can test whether or not it's greater than specification. Okay, that you'd be happy about that. If you're receiving it, you're going to be worried about it's under spec. Okay. All right, so I need to adjust my point of view here. Okay. What do we used to say about that? Okay, we have IQ scores. If a certain test is to have a mean of 100, you have a random sample of 68 students attend a series of coaching classes before taking the test. Let us assume that the average IQ is if every student mu be the population mean IQ. That would occur if every student took the coaching classes. Classes are successful if the mean is bigger than 100, and a test is made to see whether or not. So yeah, what we're doing here is, they took the coaching classes, and did the coaching classes make a difference? Okay, did they get people? If they took these classes, did they appear as if they have a higher IQ? Right? Did they score higher on this test? All right. So a test, okay, versus a test H1 greater than. Okay, so we want to test. Is it more than? Did the coaching classes have an effect? Okay, 3 possible conclusions. Classes are successful, classes are not successful, and the classes might not be successful. Beautiful. Okay. Which of the 3 conclusions is best if HO is not rejected? Okay, so remember what HO says. HO says it's the status quo. So HO says mean is still 0. Okay. HA could be any number of these things, but the mean is going to be, it's 100. Okay. So if HO is not rejected, the best result is like these coaching classes don't do anything for you. Okay. So I would say 3. I have a feeling it's 2. They're not successful. Okay. But it's probability class, right? So you always want to might is usually a better answer. So I'm going to say 3. Okay. Hedging my bet that they're going to say 2. Okay. Okay. Assume the classes are not successful, which means they scored lower. Okay. Is it possible to make a type 2 error? Of course it is. It's always possible to make a type 2 error. All right. So let's see here. What is, in this context, what is a type 2 error? Okay. So what are we doing here? Let's go back to our setup. Okay, the truth is, okay, the truth is that they really aren't there. Okay, so H1, HO, there's no difference. HA, there is a difference. Okay, or it's better. Okay, so there is a difference, but we took the test, we got 100. Like, great, there it is. So, oh no, we didn't. Guilty. So this is going to be type 2 error is we have accepted. We've accepted the HO when the alternative is actually true. So in fact, they did help. Okay, but whatever it was, maybe they didn't have coffee, maybe they had a bad day, they have fever, they had a harder test than usual, whatever. Okay, so type 2 error is like the test was effective, but we failed, but the observer failed to measure that. Okay. So yes, you can make a type 2 error. It's possible. The classes are not successful when the hypothesis is the null hypothesis is false. More. All right. Well, these are going to be long. I know. Assume the classes. Oh, reading the whole thing might be helpful. So the classes were not successful. Okay, the truth is, classes not successful. Okay, classes are not successful. They don't help at all. All right, to make a, let's go back up and look at it. So to make a type 2 error, okay, the classes were useless. Okay, but you didn't find for that. You found so this, okay, the status quo is they are effective. Okay, we're going to say that, well, no, we're not. We're going to say that they weren't. They were not effective. That's RHO. That's how you set this up. Say, nope. HO mu is equal to 100. HA mu is not equal to 100 or worse. But they were worse. Actually, those coaching classes made you do poorly on a test. Okay. So let's see here. Okay. Test. Okay. Assume the classes were not successful. It's possible to make a type 2 error. I still think it's always, but I guess since we are looking at the type 2 errors, like we accidentally accepted something when it wasn't true. Okay. So they told us what the answer is here. Okay. No, it's not possible. Okay. The classes are not successful when the null hypothesis is true. So we're comparing our test against, like, it's not helpful. It's not effective. And the null hypothesis, right? They can't be successful when this is true. Okay. So there's a thing for us. All right. So that's kind of the, the rhyme and reason behind doing a test of hypothesis here. Okay. Again, I'm not asking you those kinds of questions. Okay. Homework does a very good job of doing that, but it's also really difficult. It's difficult wording and difficult to put into a test and like feel as if I fairly tested you. Okay. So if you're having trouble with that for a little bit, okay, understand that that's not coming back on you this class. Okay, like many things in many classes, like the second time you see it, it'll go a little bit better. Okay, so if you take psychology statistics, you'll see it again. Okay, so I'm going to let you go with that, and we will do 9.2 test of hypothesis with standard deviation known in the next video. All right, let's be done.